Hello, my name is Isoo and I am currently a PhD student at UNIST Embedded AI Lab. In this presentation, I would like to introduce on-demand federated learning, the solution for federated learning on arbitrary target distributions. In this presentation, we will start with the introduction, give a brief overview, and explore on-demand federated learning and its performance. Let's begin with the introduction. In a situation with multiple clients and a server, traditional centralized learning typically gathers all the client data to the server to train a single global model. However, this requires a lot of communication cost and also raises privacy issues. Federated learning is a new deep learning model training paradigm designed to address these issues. In federated learning, local clients do not transmit their data to the server. Instead, the server will receive their local model parameters trained with their local data. The server aggregates them to generate a global model. Therefore, federated learning preserves privacy and reduces communication cost. However, in federated learning, data heterogeneity degrades the performance of the model. Because of this, many existing approaches have tried to solve this problem. One of these approaches is personalized federated learning. It trains task models tailored to local clients instead of a single global task model. In a similar context, clustered federated learning groups local clients with similar task model into clusters and generate a task model for each cluster. These methods show good performance per local dataset, but have the drawbacks of being optimized only for the limited data distribution of local clients. To address these issues, we propose on-demand federated learning. The goal of on-demand federated learning is to train the task model for arbitrary target distribution. We regard the diverse local client data as a collective pool of a rich dataset and generate a subset of clients to train the on-demand model for the target distribution. For example, as shown in the figure, if a target distribution is given, we select the two clients whose data distribution can compose the target distribution. By using fewer clients to compose subset, we enable more efficient federated learning. The steps of on-demand federated learning are as follows. First, the server receives the target distribution from the user or application. We use class distribution as the data distribution because it is intuitive and easy to handle. To train a model tailored to the user-specific target distribution, we need to compose a subset of clients based on their local data class distributions. Since class distribution is also private information, we do not share it directly. Instead, we propose a class distribution predictor to estimate the class distribution based on the information provided by the client. The class distribution predictor is trained with the task model during federated learning. It takes the gradient of the last layer of the task model as input and outputs the class distribution of the task model's input data. Once we have predicted the local class distributions, we select the clients needed to compose the target distribution. The blue box represents the target class distribution. The green box, columns of the matrix, represent the predicted class distributions of a client. And the yellow box represents the weights we need to find to compose the client subset. This can be solved as a non-negative linear square problem. Once the weights are calculated, we form the client subset with the client corresponding to the indices of the weight greater than 0. Finally, we start the on-demand federated learning with the selected clients. In this page, we will compare our method with others. That is federated averaging. This also corresponds to our baseline. And that is clustered federated learning. And that is federated multitask learning. The FedFOMO is a type of personalized federated learning, and that is ours, on-demand federated learning. When you mention GT in the parentheses, it means we're using actual values of client class distributions, not predictions. And we also compare several methods at 3 heterogeneity setting. The parameter alpha represents the heterogeneity of the data. A smaller alpha indicates a higher level of heterogeneity, resulting in a more non-IID distribution. The TD means the target distribution. These 4 TDs represent the target distribution utilized. Each cell represents a class, and the color represents the number of samples. The darker the shade, the greater the number of data samples. On-demand federated learning outperforms in heterogeneous data distribution and provides comparable performance in a more homogeneous data distribution. On-demand federated learning achieves this performance using up to 9.1 times fewer clients than other algorithms. On-demand federated learning not only achieves high performance with fewer clients, but also converges quickly. As shown in the figure, compared to other algorithms, on-demand federated learning reaches peak performance after peer communication launch. That is conclusion. In this presentation, we introduce on-demand federated learning that optimizes a deep neural network for an arbitrary target class distribution. To estimate the class distribution of clients, we propose the class distribution predictor that takes the weight gradient of the local model on a client. The evaluation shows ours achieves up to 5% higher accuracy on the target distribution using 9 times fewer clients compared to the other sort of federated learning method. Thank you for listening.